Alright, let's have a look at the probability space factoring theorem. This one is exciting. So, what do we assume? Well, suppose we let A and B1 through Bn, where n is a natural number, but admittedly, it is infinity. This sequence may be finite or infinite, doesn't matter. Let them be random events satisfying the following, such that 1. The probability of the union of all the bn's is 1. In other words, they cover the entirety of the probability space, but we're not finished. We also require that they are pairwise disjoint. Symbolically, that bi intersected with bj is the empty set whenever I is different from j. So in other words, bn's in a certain way factor the probability space, hence the name. Then the probability of A, which is any random event whatever, is equal to the this was unfortunate to choose is equal to the sum ranging through m to n of the probabilities of A under the condition of the individual BMs multiplied by the probability of BM of the condition. So, multiplied by the probability of the condition. Now, how do we prove this? Well, as all proof so far, it is trivial. Well, we observe that we can write PA equal to PA of, P of A intersected with the union of all the BNs united with united with A intersected with the complement of this set. This is nothing clever and nothing new. All this says is that A can be written as the intersection of some set and the intersection of A and the complement of the set. This isn't interesting, but we can put this, we know that this is equal to P of A intersected with the union ranging through 1 to n, but we also use n to index because we have very unfortunately named the final bn plus this I can write by the sigma additivity of probability, since it is a measure A intersected with the union Bn complement. But if we really think about it, this is 0. Why? Well, since Bn cover the entire space, well then the complement must be quite small, and if we intersect it with A, it is even smaller than that. Meaning this is some set of measure 0, and hence the probability is 0. So we can ignore the second addend and simply write P of A intersected with UNB But using the De Morgan rules, we know that this is equal to the union of the intersections Bn, A. But we know that the individual Bn's are disjoint, and therefore their intersections with A are also disjoint, and thus we can use again the sigma additivity of measure, and we can write then that this is equal to the sum, with n as the iterator, still unfortunately named, as the sum of the individual probabilities of Bn intersected with A. But of course we can write this out simply as the probability of imagine we swap them around, the probability of A under the condition of Bn times the probability of the condition. This follows from the definition of a conditioned probability, which we can write here in the corner. So the conditioned probability of x under the condition of y is equal to the probability of x intersected with y divided by the probability of y. So simply by multiplying this identity by the probability of y, we obtain the desired, we get our claim. And this concludes the proof.